For most of the history of astronomy, the center of our galaxy was a mystery hidden behind an impenetrable wall of dust. Even after radio telescopes revealed something extraordinary lurking there, no one could see it directly. All astronomers could do was watch the stars around it, and the more closely they watched, the stranger the story became. At the exact center of the Milky Way, 26,000 light years from Earth, sits an object containing the mass of more than 4 million suns, compressed into a region smaller than the distance between the Earth and the Sun. Every one of the galaxy's hundreds of billions of stars, including our own Sun, is ultimately orbiting it. In 2022, the Event Horizon Telescope finally captured the first image of this mysterious object. A glowing ring surrounded a circle of perfect darkness. It appeared to confirm what physicists had predicted for decades. Then the questions began. Stars race around it at speeds reaching roughly 2.5% of the speed of light, fast enough for Einstein's predictions about time itself to become measurable. A cloud of gas that should have been torn apart survived its close encounter. Young stars somehow exist where gravity should prevent stars from forming at all, and despite possessing the mass of millions of suns, the object remains astonishingly quiet, producing only a tiny fraction of the energy astronomers expect. Even more unsettling, some researchers now argue that the famous image may not prove what the world believes it does. Quick favor before we continue. If you find yourself coming back to videos like these, hit subscribe so you don't miss the next one. It makes a bigger difference than you might think. Now, let's begin with how astronomers first discovered that something invisible was hiding at the heart of the Milky Way. The first real glimpse of the Milky Way's heart did not come through an eyepiece. It arrived as an unexpected pattern hidden inside radio interference, discovered while someone was trying to improve long distance communication across the Atlantic Ocean. Sometimes the path toward the greatest discoveries begins far from the questions we think we are asking. Between Earth and the center of our galaxy stretches about 26,000 light years, a distance that is nearly 153,000 trillion miles. That immense corridor is crowded with gas, dust, and interstellar material that absorbs visible light so effectively that ordinary optical telescopes cannot peer through it. For generations, astronomers could map much of the galaxy while its central region remained concealed behind this natural veil. Everything changed during the early 1930s. Karl Jansky, a radio engineer working at Bell Telephone Laboratories in New Jersey, was investigating persistent radio static disrupting transatlantic telephone transmissions. As he rotated his large antenna across the sky, one source kept returning with remarkable consistency. The signal followed the stars rather than Earth's daily activity, revealing that its origin lay far beyond our planet. His conclusion reshaped astronomy. In 1933, Jansky published his findings after tracing the mysterious radio waves toward the constellation Sagittarius, the direction of the galactic center. That single observation gave birth to radio astronomy, the study of the universe through radio waves instead of visible light. Suddenly, regions hidden behind cosmic dust became accessible through an entirely different window. But the brightest source still needed a name. During 1974, astronomers Bruce Balick and Robert Lee Brown used the Green Bank Interferometer in West Virginia to identify an unusually compact and energetic radio source at the very center of the Milky Way. Brown named it Sagittarius A star. The word star came from a notation used in atomic physics to indicate an excited energetic state, reflecting the exceptional strength of the radio emission rather than describing an ordinary star. The mystery deepened as technology improved. Throughout the 1980s and 1990s, Infrared observatories began tracking individual stars packed closest to Sagittarius A star. Infrared light has longer wavelengths than visible light, allowing much of it to pass through dust that normally blocks our view. Those stars, later known collectively as the S stars, followed paths that demanded an invisible gravitational anchor of extraordinary mass. Two research teams spent decades measuring those stellar motions with extraordinary precision. Reinhard Genzel led one effort at the Max Planck Institute in Germany. Andrea Ghez directed the other at the University of California, Los Angeles. Working independently, both groups reached the same conclusion before the end of the 1990s. More than 4 million suns worth of mass occupied a region far too small for any known object except a supermassive black hole. Their achievement earned the Nobel Prize in Physics during 2020, the first award recognizing direct evidence for a supermassive black hole. But establishing its existence only opened a far deeper investigation into the remarkable behavior of the object itself. Some of the fastest journeys in our galaxy unfold inside a region that seems impossibly small. The innermost light year surrounding Sagittarius A star would fit comfortably between our Sun and Proxima Centauri, the nearest neighboring star. Yet within that confined space, a compact family of brilliant young stars races through gravity so intense that every completed orbit becomes another experiment performed by the universe itself. The best known member of this remarkable group is S2. Some scientific papers from the United States also refer to it as S02, but both names describe the same star. Since the early 1990s, astronomers have followed its motion with extraordinary precision. While our Sun requires about 225 million years to circle the Milky Way, S2 completes one full elliptical orbit around Sagittarius A star in only about 16 years. You can witness meaningful changes during a single scientific career. Its nearest approach is breathtaking. Astronomers call that closest point periapsis, the moment when an orbiting object reaches its minimum distance from the body it circles. At periapsis, S2 passes within about 120 astronomical units of Sagittarius A star. One astronomical unit is the average distance between Earth and the Sun. During that brief passage, the star accelerates to roughly 7,650 kilometers every second, which is about 4,754 miles every second. But gravity begins changing more than speed. As S2 climbs away from the enormous gravitational field, its light stretches toward longer wavelengths through an effect called gravitational redshift. In simple terms, the escaping light loses a tiny amount of energy before reaching us. Its orbit also experiences Schwarzschild precession, meaning the ellipse slowly rotates after every revolution instead of repeating exactly the same path. These subtle changes match the predictions of Albert Einstein's general theory of relativity with remarkable accuracy during the star's periapsis passage in 2018. It became the strongest direct test of the theory ever performed around a supermassive black hole. Other stars press even deeper into this extreme environment. The star known as S62 circles Sagittarius A star in less than 10 years, giving it the shortest confirmed orbital period of any known star around a galactic center. Near periapsis, it exceeds 1/10 of the speed of light. Another candidate, designated S4714, may travel even closer, approaching only about 12 astronomical units while reaching nearly 8% of light speed, although astronomers continue refining those measurements. Yet one mystery overshadows every orbit. These stars are young, hot, and massive, exactly the kind expected to form inside collapsing clouds of gas. Near Sagittarius A star, powerful tidal forces, meaning differences in gravity across a cloud, should pull those clouds apart before star formation can even begin. But the S stars exist anyway, whether they formed elsewhere before migrating inward or somehow emerged within this hostile region itself, remains one of the deepest unresolved puzzles at the heart of our galaxy. For many years, the object at our galaxy's center existed only through mathematics. We watched nearby stars bend, accelerate, and curve through space, then worked backward to infer the hidden source shaping every orbit. No telescope had ever produced a direct view of the object itself. That changed after one of the most ambitious observing campaigns ever attempted. The instrument responsible was far larger than any single observatory. The Event Horizon Telescope is a global network using a technique called interferometry, where many widely separated radio telescopes operate together as though they were one enormous instrument. During 2017, 8 observatories spread across Chile, Hawaii, Spain, Antarctica, and Arizona observed Sagittarius A star over several nights in April. By combining their measurements with astonishing precision, they created an effective telescope whose diameter rivaled that of Earth itself. The observations generated an overwhelming amount of information. Roughly 5 petabytes of recorded data filled stacks of specialized storage drives. A petabyte equals about 1 million gigabytes. The files were so immense that transmitting them across the internet would have taken far too long. Instead, the drives were physically transported by aircraft to processing centers, where synchronized atomic clocks allowed researchers to combine every observation into a single dataset. But collecting the information was only the beginning. During May of 2022, the collaboration released the first image of Sagittarius A star. The picture revealed a glowing ring surrounding a dark central region measuring about 51.8 micro arcseconds across. A micro arcsecond is an incredibly small unit of angular measurement. The resolution was so extraordinary that it resembled identifying a donut resting on the surface of the moon while viewing it from Earth. The image carried an important distinction. The brilliant ring was not the black hole itself. Instead, it showed the accretion disk, a rapidly circulating flow of intensely heated gas and plasma spiraling inward under overwhelming gravity. The dark center represented the black hole's shadow, the region where gravity bends and captures light so completely that no direct illumination reaches us from within its boundary. Even obtaining this image proved unusually difficult. Sagittarius A star contains far less mass than the giant black hole at the center of the galaxy. Messier 87, making its surrounding gas evolve over minutes instead of days. Imagine photographing a child sprinting across a playground while leaving the camera shutter open for hours. The target keeps changing throughout the exposure, making every observation far harder to reconstruct. Sophisticated machine learning techniques helped solve that challenge. Machine learning allows computer systems to recognize patterns within enormous data sets without following a single fixed instruction for every possibility. Researchers produced 4 completely independent image reconstructions, each arriving at remarkably similar results that matched the predicted appearance of a rotating black hole. But scientific agreement never marks the end of investigation. Within months, several independent studies began examining whether the observed ring could also be explained by more exotic possibilities, reminding us that even humanity's clearest portrait of the galactic center still leaves room for profound debate. There is a striking contradiction at the center of the Milky Way. Everything we have measured tells us Sagittarius A star possesses the mass expected to power one of the brightest engines in the nearby universe. Yet, when we examine the energy actually reaching our telescopes, we find an object producing only a faint fraction of what standard theory predicts. The numbers simply refuse to match expectation. Across the universe, many galaxies host what astronomers call active galactic nuclei. This term describes galactic centers where supermassive black holes consume large amounts of surrounding material. As gas spirals inward, enormous gravitational energy transforms into heat and radiation, allowing some of these objects to outshine every star in their host galaxy combined. A few remain visible across billions of light years. But Sagittarius A star behaves very differently. Its measured luminosity, meaning the total energy it radiates every second, is only about 1 undecillion ergs each second, roughly 400 times the luminosity of our Sunday. Although that sounds extraordinary, a black hole containing more than 4 million solar masses should shine roughly 10,000 times more brightly if it were feeding at even a modest pace. Instead, it barely consumes anything. Astronomers estimate Sagittarius A star swallows only about 1/10,000th of a solar mass each year. That feeding rate appears astonishingly low because the surrounding environment contains no shortage of material. Within the central parsec, a parsec being about 3.26 light years, which is about 19.2 trillion miles, powerful stellar winds continuously pour gas into the region from nearby massive stars. Computer simulations suggest that only about 1% of this available material actually reaches the event horizon. One leading explanation is called an advection-dominated accretion flow. This describes gas becoming so hot and diffuse that it struggles to radiate energy efficiently. Much of the inflowing material is then driven back outward before gravity can pull it all the way inward. The model explains many observations, yet important details still resist complete understanding. But a recent discovery added another piece to the puzzle. During June of 2026, astronomers announced the first direct detection of a wind flowing outward from Sagittarius A star after roughly 50 years of searching. The observation confirmed that material really is escaping instead of falling inward. That finding supports the existing picture while introducing another mystery. What powers this persistent outward flow if so little matter reaches the central object? The contrast becomes even more remarkable when we compare our galactic center with the giant black hole inside the galaxy Messier 87. That object contains about 6.5 billion solar masses and launches an immense jet of plasma stretching roughly 5,000 light years into space. Sagittarius A star shows no confirmed jet approaching that scale. You and I are left observing an object surrounded by abundant fuel, possessing extraordinary gravity, yet refusing to behave like the brilliant cosmic engine theory tells us it should become. Most of the time, Sagittarius A star releases surprisingly little energy for an object of its immense mass, but every so often, that steady pattern changes without warning. For a brief period, the region surrounding the event horizon erupts with an intense flash of radiation before settling back again. These sudden outbursts are known as flares, and they offer one of our closest glimpses into the restless environment surrounding the hidden center. The first dramatic flare arrived at the beginning of this century. During 2000, the National Aeronautics and Space Administration Chandra X-ray Observatory detected a powerful burst lasting about 3 hours. Throughout that event, the X-ray brightness increased by roughly 45 times compared with its usual level. Nothing similar had ever been observed from Sagittarius A star before, immediately revealing that the object could shift from relative inactivity to remarkable brilliance within only a short time. Since then, astronomers have found these events occur far more often in infrared light. Infrared flares usually appear between 1 and 4 times each day. Some last only about 30 minutes, while others continue for several hours. During the strongest events, the infrared brightness can rise more than 75 times above its normal value before fading once again. Each flare provides another opportunity to examine physical processes unfolding almost at the edge of the event horizon. One observation proved especially memorable. During May of 2019, astronomers using the Keck Observatory in Hawaii recorded the brightest infrared flare ever seen from Sagittarius A star. The outburst became so luminous that astronomer Tuan Du initially believed he was observing the nearby star S2 instead. Within roughly 2 hours, the flare reached nearly 75 times the object's typical brightness, becoming one of the most extraordinary changes ever measured at the galactic center. But the engine behind these bursts remains uncertain. One leading explanation involves magnetic reconnection. This process occurs when tangled magnetic field lines suddenly break apart and reconnect, releasing enormous amounts of stored energy in an instant. Other researchers suggest brief instabilities within the innermost accretion disk, or even small objects wandering too close before being torn apart by gravity. Current observations support several possibilities, yet none explains every detail. The location of these flares appears remarkably confined. They originate within only a few Schwarzschild radii of the event horizon. The Schwarzschild radius is the distance from the center at which the event horizon forms around a non-rotating black hole. For Sagittarius A star, that radius measures about 12.4 million kilometers, which is about 7.7 million miles, slightly smaller than the radius of our Sunday. Their rapid changes reveal something equally important. Since the brightness rises and falls within only a few minutes, the emitting region cannot be larger than the distance light travels during that brief interval. Observations across infrared and radio wavelengths also reveal a consistent delay of about 20 minutes. Energetic particles appear to radiate infrared light first, then gradually cool before producing radio waves, allowing you and me to watch the same event unfold across different forms of light, while the underlying physics continues to challenge our understanding. Astronomy occasionally presents a prediction that appears almost certain. Every calculation agrees. Every simulation reaches the same conclusion, and years of observation seem ready to confirm it. Then nature chooses a different path. That was exactly what unfolded when an unusual object drifted toward Sagittarius A star. During 2002, astronomers identified an elongated cloud of gas and dust moving through the region surrounding the galactic center. They named it G2. Careful measurements showed that its orbit would carry it extremely close to Sagittarius A star, placing it directly inside one of the most destructive gravitational environments in the Milky Way. The forecasts sounded dramatic. Studies published during 2011 and 2012 predicted that G2 would not survive its closest approach. Powerful tidal forces, meaning differences in gravity across the object's length, were expected to stretch the cloud into a long filament before tearing it apart completely. As the debris spiraled inward, astronomers anticipated a brilliant flare that would briefly transform Sagittarius A star into a far more energetic source of radiation. Observatories around the world prepared for the encounter. Early in 2014, G2 reached periapsis, the closest point in its orbit around Sagittarius A star. At that moment, it passed within roughly 130 astronomical units of the central object. One astronomical unit is the average distance between Earth and the Sunday. Researchers watched carefully, expecting the predicted fireworks. They never arrived. Sagittarius A star showed remarkably little change, and G2 continued its journey instead of disappearing. The object had survived an encounter that many believed would destroy it. The result forced astronomers to reconsider nearly every assumption they had made about its nature. But G2 was never an ordinary gas cloud. Later observations indicated that a compact stellar core lay hidden inside the surrounding envelope of gas and dust. One leading idea suggests this core formed after two stars merged into a single object. That dense central body provided enough gravity to hold the surrounding material together while passing through tidal forces that would have dispersed an unbound cloud almost immediately. Even more surprising discoveries followed. Astronomers eventually identified several related objects, designated G1 through G6, each sharing similar orbital characteristics and similar mixtures of stars, gas, and dust. During 2025, observations using the Enhanced Resolution Imager and Spectrograph instrument on the Very Large Telescope confirmed that four of these unusual objects, including G2 and a binary system called D9, remain in stable long-term orbits rather than slowly falling inward. Their existence reshapes our picture of the galactic center. These objects are more durable and structurally complex than existing theories predicted. They suggest that the environment surrounding Sagittarius A star supports forms of stellar evolution and gravitational survival that astronomers had not anticipated. Instead of finding a region where only destruction dominates, you and I discover a place where unexpected structures endure against extraordinary odds. Far beyond the crowded heart of our galaxy, an invisible monument stretches into space. You cannot see it through ordinary telescopes, and for countless generations, nobody even suspected it existed. Yet it towers above and below the Milky Way, preserving the memory of an event powerful enough to reshape our entire galactic home. The discovery arrived during 2010, when the National Aeronautics and Space Administration launched observations from the Fermi Gamma Ray Space Telescope. Researchers uncovered two immense lobes of high-energy gamma-ray emission rising from opposite sides of the galactic plane. Each structure extends roughly 25,000 light-years, together spanning nearly half the visible diameter of the Milky Way. The finding surprised everyone. Earlier instruments had overlooked these enormous formations because they shine mainly in gamma rays and X-rays instead of visible light. Existing models of the galaxy had not predicted anything comparable. The structures became known as the Fermi bubbles, and almost immediately they raised an unsettling question. What could possibly have created something so vast? Calculations pointed toward an astonishing answer. Inflating the bubbles required roughly 10 to the power of 55 ergs of energy, an amount comparable to the combined output of about 100,000 supernova explosions. No ordinary process seemed capable of supplying such extraordinary power. Astronomers narrowed the possibilities to two leading explanations, each carrying profound consequences for our understanding of the galactic center. But the first possibility places Sagittarius A star at the center of the story. According to this idea, between roughly 4 million and 17 million years ago, the supermassive black hole entered a far more active phase. A substantial inflow of matter, or perhaps a powerful jet of energized particles, could have blasted material outward in opposite directions, gradually inflating the enormous bubbles we observe today. Their remarkably symmetrical geometry supports this interpretation because both structures align closely with the galactic center instead of appearing scattered across a wider region. The competing explanation looks toward the stars themselves. An intense period of star formation near the galactic center could have produced countless massive stars whose powerful stellar winds and eventual supernova explosions combined into one enormous outflow. Yet observations in the X-ray portion of the spectrum reveal remarkably sharp edges surrounding the bubbles, features that many researchers believe fit a sudden central eruption more naturally than a prolonged burst of widespread stellar activity. Fresh observations added another layer. During 2020, the German-Russian eRosetta X-ray telescope detected even larger structures, reaching about 45,000 light-years above and below the galactic plane. These enormous formations, now called the eRosetta bubbles, may represent the same ancient event unfolding on an even greater scale. If Sagittarius A star truly produced these immense structures, then the subdued object we observe today once behaved very differently. We would be looking at an engine that transformed the Milky Way before fading into its present state. But the reason for that dramatic change remains unknown, leaving you and me with a galaxy whose greatest eruption still echoes across space, even after millions of years. A single image can appear decisive, yet the path leading to that image may be far more intricate than it first seems. As we look more closely at the famous view of Sagittarius A star, you begin to discover that the greatest debate is no longer about what was observed. It is about how those observations became the picture seen around the world. Unlike an ordinary photograph, the Event Horizon Telescope image did not emerge from one camera capturing a complete scene. The telescope is a worldwide network of radio observatories that collects fragments of information from enormous distances. Those separate signals must then be combined through interferometry, a technique that merges widely separated observations into one virtual telescope the size of Earth. Even after that process, important gaps remain within the measurements. Those missing pieces matter. To reconstruct the final image, researchers relied on sophisticated computational algorithms designed to identify the most physically consistent solution permitted by the available data. The resulting orange ring matched decades of theoretical predictions for a rotating black hole. But the reconstruction itself depends upon mathematical choices, and different methods can emphasize different possibilities hidden within the same observations. But another interpretation soon appeared. During October of 2024, a team led by Makoto Miyoshi at the National Astronomical Observatory of Japan reanalyzed the original Event Horizon Telescope measurements using a different reconstruction approach. Their results suggested the galactic center should appear as an elongated and asymmetric disk rather than the familiar circular ring. Such a structure would differ substantially from the expected appearance of a rotating black hole described by the standard mathematical model. The Event Horizon Telescope collaboration strongly challenged that conclusion. Its researchers argued that the alternative reconstruction did not properly satisfy the observational constraints imposed by interferometry. According to their analysis, the original image remains the best representation supported by the data. Neither side disputes the measurements themselves. The disagreement concerns how those measurements should be transformed into a visible image. Another possibility reaches even further. During February of 2026, a team led by Valentina Crespi at the Institute of Astrophysics, La Plata, proposed that the object at the galactic center could instead be an extraordinarily dense core of fermionic dark matter. Fermions are particles that cannot all occupy the same quantum state, allowing them under certain conditions to form extremely compact structures supported by quantum pressure instead of collapsing indefinitely. If such a dense core exists, gravity would bend surrounding light strongly enough to create a shadow remarkably similar to one produced by a black hole. The familiar ring could therefore emerge without an event horizon at all. Even the measured motions of the nearby S stars would remain essentially unchanged because gravity responds to mass itself, regardless of what that mass is made from. But current observations cannot decisively separate these competing ideas. Statistical comparisons indicate that both models remain compatible with the available evidence. For now, you and we are left with an image that continues to inspire confidence, while also reminding us that science advances by testing every explanation against the same universe. Before we can weigh competing ideas about the heart of the Milky Way, we need to understand the invisible substance standing at the center of that debate. Dark matter is often described as mysterious, yet its existence is supported by decades of observations. You cannot see it directly, but its gravity leaves unmistakable fingerprints across the universe, from individual galaxies to the largest structures known. The first compelling evidence emerged during the 1970s through the work of astronomer Vera Rubin. She carefully measured how spiral galaxies rotate, expecting stars near their outer edges to move much more slowly than those closer to the center. That prediction followed naturally from Isaac Newton's theory of gravity, which says orbital speed should decrease as distance from the main concentration of mass increases. But the universe disagreed. Rubin found that stars far from galactic centers continued orbiting at nearly the same speed as stars much closer in. If only visible matter were present, those outer stars should have escaped into intergalactic space long ago. Their continued motion implied that an enormous amount of unseen mass surrounded every galaxy, providing the additional gravitational pull needed to keep those stars bound. Astronomers now describe this hidden material as dark matter. The name does not mean it is simply very dim. Instead, dark matter neither emits, absorbs, nor reflects electromagnetic radiation. The broad family of light that includes radio waves, visible light, infrared light, ultraviolet light, X rays, and gamma rays. Because it does not interact with light in ordinary ways, every attempt to observe it directly has failed. Its presence is inferred entirely through gravity acting on visible objects. Even today, its composition remains unknown. Several leading possibilities have been proposed, including weakly interacting massive particles, axions, sterile neutrinos, and primordial black holes formed shortly after the beginning of the universe. Each candidate satisfies some observations while leaving other questions unresolved. Despite increasingly sensitive experiments spanning many decades, none has been confirmed. But the model proposed for Sagittarius A star points toward a different possibility. It suggests dark matter consists of fermions, particles with masses of roughly 56 kiloelectron volts. A kiloelectron volt is a unit used to describe the energy, and therefore the mass, of extremely small particles. These fermions obey the Pauli exclusion principle, a rule stating that identical particles cannot all occupy the same quantum state. As gravity compresses them together, that rule creates an opposing pressure, preventing complete collapse into a singularity while allowing an extraordinarily dense central core to form. If this picture proves correct, the Milky Way would not be organized around a single, infinitely dense point. Instead, one continuous dark matter structure would extend from the galaxy's faint outer halo all the way to its crowded center, where its densest region resides. Such a discovery would reshape our understanding of galaxies themselves, replacing one of astronomy's most familiar foundations with an entirely different cosmic architecture. Imagine trying to determine the weight of something that never reflects light, never reveals a solid surface, and cannot be touched by any instrument. That is exactly the challenge astronomers faced at the center of our galaxy. Yet, through decades of patient observation, they have measured the mass of Sagittarius A star with astonishing precision. You and we never see the object itself in the ordinary sense. Instead, we witness gravity shaping the motions of everything around it. The most accurate measurement comes from the remarkable orbit of the star, known as S2. For more than 30 years, astronomers have followed its path across the sky, recording every subtle change in its position and speed. Its orbital period, elongated shape, closest approach, and the slight turning of its orbit predicted by Albert Einstein's general theory of relativity together create an extraordinarily detailed gravitational fingerprint. When these observations are matched against mathematical models based upon Isaac Newton's and Albert Einstein's laws, they reveal a central mass of approximately 4.15, 4 million times the mass of our Sun, with an uncertainty smaller than 1/2 of 1%. But another quantity emerges at the same time. The distance to Sagittarius A star is measured alongside its mass because the apparent size of the orbit, combined with the star's true velocity and orbital period, links both values together. Current observations place the galactic center about 26,673 light years away from Earth, equivalent to roughly 8,178 parsecs. A parsec is an astronomical distance based upon the apparent shift of a nearby star as Earth travels around the Sunday. Once the mass is known, another remarkable property follows naturally: the Schwarzschild radius, meaning the event horizon radius of a non-rotating black hole, increases in direct proportion to mass. For Sagittarius A star, that radius is approximately 12.4 million kilometers, which is about 7.7 million miles. Surprisingly, that distance is still slightly smaller than the radius of our own Sunday. The comparison becomes even more striking. Our Sun spans about 696,000 kilometers, which is about 432,473 miles. If it somehow collapsed into a black hole, all of that mass would need to fit inside a sphere only about 3 kilometers across. That is nearly 2 miles. Gravity alone would remain. Everything else would disappear beyond the event horizon. Packing more than 4 million solar masses into such a compact volume implies an average density of roughly 1 quintillion kilograms per cubic meter, around 1 quadrillion times denser than water. But alternative ideas, including dense dark matter cores, gravastars, boson stars, and wormhole entrances, must reproduce every one of these measured gravitational effects, while also matching the observed image reconstructed by the Event Horizon Telescope. The mass itself is no longer the mystery. The true nature of the object producing that immense gravitational field still is. Perspective changes everything. After spending time beside the hidden heart of our own galaxy, we can finally step back and see where Sagittarius A star belongs among the immense population of cosmic giants. It is an extraordinary object by human standards, yet across the universe it occupies a surprisingly modest place. You and we have been examining something immense, but the universe contains many engines that make it appear almost restrained. Ordinary stellar mass black holes, formed from the collapse of massive stars, usually contain between about 3 and 50 times the mass of our Sunday. Sagittarius A star outweighs them all by an astonishing margin, containing roughly 4.154 million solar masses. That enormous figure places it within the family known as supermassive black holes, objects that reside near the centers of most large galaxies and shape their surroundings through gravity over millions of years. But some members of that family grow far larger. At the center of the galaxy, known as Messier 87, lies a supermassive black hole containing approximately 6.5 billion solar masses, more than 1,500 times the mass of Sagittarius A star. Unlike the calm behavior we observe in our own galactic center, this giant launches a narrow jet of plasma stretching nearly 5,000 light years through space. The material races outward at speeds approaching the speed of light, carrying enormous amounts of energy far beyond its host galaxy. Even that is surpassed elsewhere. The distant quasar, called TON 618, located about 10.4 billion light-years from Earth, is estimated to contain a black hole of roughly 66 billion solar masses. Another remarkable candidate, Phoenix A, may harbor between 50 billion and 100 billion solar masses, although those estimates still carry significant uncertainty. These colossal objects belong to galaxies whose central regions blaze with extraordinary brilliance. Their power comes from feeding. Quasars are galaxies whose central supermassive black holes consume matter at astonishing rates, releasing enough energy to outshine entire galaxies containing hundreds of billions of stars. Sagittarius A star currently gathers material at a rate millions of times lower, but this subdued state is not unusual for the present era of cosmic history. Around 10 billion years ago, the universe contained far more gas available for consumption, allowing quasars to flourish across space. Today, many large galaxies host central black holes that have entered comparatively inactive phases. What truly distinguishes Sagittarius A star is something much simpler. It is close. At a distance of about 26,000 light-years from Earth, it is the nearest known supermassive black hole by an overwhelming margin. That proximity allows us to track individual stars, measure gravity with exceptional precision, and examine its surroundings in ways impossible for more distant galaxies. By comparison, the supermassive black hole at the center of the Andromeda Galaxy lies about 2.5 million light-years away, nearly 100 times farther from us. But because our own galactic center rests within observational reach, each improvement in technology brings us closer to examining regions only a few Schwarzschild radii across, revealing details that remain forever beyond reach around more distant cosmic giants. Across the universe, many supermassive black holes announce their presence with astonishing displays of power. They launch narrow beams of blazing plasma that pierce through their host galaxies, carrying energy across distances that dwarf entire stellar systems. After everything we have learned about Sagittarius A star, you might expect to find a similar structure emerging from the center of the Milky Way. But we do not. These structures are known as relativistic jets. A relativistic jet is a tightly focused stream of electrically charged particles traveling at speeds close to the speed of light. The leading explanation for their formation is called the Blandford-Znaic mechanism. In simple terms, powerful magnetic fields surrounding the accretion disk interact with the spinning black hole, drawing rotational energy from it, and directing that energy into two opposing beams, extending far into intergalactic space. Some galaxies provide spectacular examples. The supermassive black hole in Messier 87 drives a jet stretching nearly 5,000 light-years from its galactic center, visible from radio waves through gamma rays. The central black hole of Centaurus A powers jets reaching approximately 13,000 light years. The famous quasar, known as 3C273, produces an even greater structure, extending about 200,000 light years across space. These immense outflows reveal black holes actively converting gravity into extraordinary displays of energy. But Sagittarius A star remains different. No confirmed relativistic jet of comparable scale has ever been detected. Radio observations have revealed intriguing hints of compact outflows, and the recently confirmed outward blowing wind demonstrates that material does escape the region surrounding the central object. Yet, these observations fall far short of the long, highly organized jets seen in active galactic nuclei. Something appears to interrupt the process before such structures can fully develop. One possibility centers on the remarkably low accretion rate. Jets may require a steady supply of infalling gas to maintain the magnetic field geometry necessary for launching and sustaining them. If too little material reaches the accretion disk, the magnetic fields may never become strong or stable enough to produce a large-scale beam. But another possibility shifts attention toward the central object itself. If Sagittarius A star rotates only slowly, far less rotational energy would be available for extraction through the Blandford-Znajek mechanism. Current estimates of its spin remain uncertain, ranging from almost non-rotating to moderately rotating, making this one of the highest priorities for future observations by the Event Horizon Telescope. Yet, one clue refuses to disappear. The immense Fermi bubbles rising above and below the Milky Way remain difficult to ignore. Their overall geometry resembles the pattern expected from a pair of powerful jets that once blasted outward from the galactic center. If Sagittarius A star truly generated those structures millions of years ago, then the conditions required for jet formation clearly existed in the past. But those conditions no longer prevail, leaving us with a central engine whose greatest mystery may not be what it is doing today, but how profoundly its behavior has changed. Some mysteries depend upon what an object is made of. Others depend upon how it moves. As we continue circling the hidden center of the Milky Way, another question comes into view. Does Sagittarius A star remain almost motionless within its own gravity, or is it spinning at tremendous speed, carrying space-time itself along with it? According to the no-hair theorem of Albert Einstein's general theory of relativity, every black hole can be described by only three fundamental properties. These are mass, spin, and electric charge. The theorem states that every detail about the matter that originally collapsed to form the black hole disappears behind the event horizon, leaving only those three measurable characteristics. For real black holes in space, electric charge is expected to become almost non-existent because surrounding particles carrying opposite charges are quickly attracted, canceling any imbalance. Mass has already been measured with remarkable precision, but spin remains far more elusive. Astronomers describe spin using a quantity known simply as the spin parameter. This number ranges from 0 for a completely non-rotating black hole to 1 for the fastest rotation theoretically allowed by Albert Einstein's equations. A non-rotating object is called a Schwarzschild black hole, while a rotating one is known as a Kerr black hole. Current estimates place the spin of Sagittarius A star somewhere between almost 0 and approximately 0.9. Such a broad range reveals how difficult the measurement truly is. Rotation changes everything nearby. A spinning black hole drags space-time around with it through an effect known as frame dragging, also called the Lentz-Thirring effect. In simple terms, the very fabric of space and time becomes twisted by the object's rotation. Paths followed by light, orbiting stars, and even freely moving gyroscopes gradually shift because spacetime itself is no longer standing still. These subtle distortions offer valuable clues. The spin influences the innermost regions of the accretion disk, alters the long-term motion of nearby stars, affects the polarization of infrared flares, and changes the detailed appearance of the shadow reconstructed by the Event Horizon Telescope. Polarization describes the preferred orientation of light waves, allowing astronomers to trace the geometry of magnetic fields surrounding the event horizon. Several studies of these infrared flares suggest that Sagittarius A star may rotate at a moderate or even rapid rate, but those conclusions depend upon assumptions about the behavior of the surrounding gas that remain uncertain. If the spin approaches its maximum possible value, another remarkable region appears. Outside the event horizon lies the ergosphere, a zone where space-time is dragged so strongly that nothing can remain motionless with respect to distant observers. Within this region, theoretical models allow rotational energy to be extracted, providing the power needed to launch enormous relativistic jets. Whether Sagittarius A star possesses such an energetic ergosphere remains uncertain, because its true rotation has not yet been pinned down. Future observations may finally narrow the possibilities. Higher resolution measurements from the Event Horizon Telescope, together with proposed space-based interferometry missions, could reveal tiny asymmetries within the accretion flow on scales smaller than the Schwarzschild radius itself. But until those observations arrive, the spin of Sagittarius A star remains one of the last fundamental properties still waiting to be measured with confidence. Some discoveries challenge our understanding through sheer size. Others do so simply by existing. As we follow the crowded heart of the Milky Way, we encounter a population of stars that appears to ignore one of the most fundamental rules of gravity. They shine exactly where many astronomers believe they should never have been born. Within the innermost zero point 0.5 light-years of the galactic center, astronomers have identified roughly 200 young, massive stars belonging mainly to the O and B stellar classes. These brilliant blue stars burn through their fuel with extraordinary speed, surviving only a few million years before ending their lives as powerful supernova explosions. Their youthful spectra leave little room for doubt. They formed recently by cosmic standards, but their location creates an extraordinary puzzle. Sagittarius A star exerts immense tidal forces throughout this region. Tidal forces arise because gravity pulls more strongly on the side of an object nearest the central mass than on the far side, stretching anything caught within the difference. Under such conditions, giant clouds of molecular gas should struggle to collapse into new stars. Beyond the Roche limit, which marks the point where tidal stretching overwhelms an object's own gravity, fragile clouds are expected to be torn apart before star formation can begin. The numbers become even harder to accept. For a gas cloud to resist disruption only zero point 0.5 light-years from Sagittarius A star, it would need an internal density far beyond what known processes are expected to produce within this environment. Existing models fail to provide an obvious path towards such extreme compression, yet the stars remain exactly where observations place them. Astronomers call this contradiction the paradox of youth. One proposed explanation suggests these stars formed much farther from the galactic center before gradually drifting inward. This process, known as dynamical friction, occurs when massive objects lose orbital energy through countless gravitational interactions with surrounding stars and gas. Over time, they spiral closer to the center. But detailed calculations indicate that such a journey should have continued until many of these stars disappeared into Sagittarius A star itself, rather than settling into the stable orbits we observe today. Another possibility shifts the birthplace instead of the journey. Several researchers suggest that about 6 million years ago, a massive disk of gas surrounded Sagittarius A star. If dense enough, portions of that disk might have overcome the destructive tidal forces locally, allowing stars to form in place before the gas later dispersed. Some patterns within today's stellar distribution offer limited support for this scenario, but another complication soon appears. The innermost S stars, orbiting within 0.04 light years, do not share a common orbital plane. Instead, their paths point in many different directions, implying either several separate episodes of star formation or an earlier period of intense gravitational encounters that scattered their original orbits. After more than 25 years of careful study, this remarkable stellar population continues to resist every complete explanation, reminding us that even the closest supermassive black hole still keeps some of its deepest histories beyond our reach. The Milky Way does not carry its history in ancient ruins or weathered landscapes. Instead, it preserves enormous scars made from radiation, plasma, and invisible energy stretching far beyond the stars we can easily see. As we look outward from our own position, you begin to recognize that the calm galaxy surrounding us may simply be the lingering result of an extraordinary chapter that unfolded only a few million years ago. Today, Sagittarius A star consumes remarkably little material. Its surroundings appear restrained compared with the brilliant centers of many distant galaxies, but enormous structures rising above and below the galactic disk tell a very different story. The most striking are the Fermi bubbles, discovered in the year 2010, each extending roughly 25,000 light-years from the galactic center. Together, they span nearly half the visible diameter of the Milky Way. Their scale is astonishing. Calculations indicate these giant lobes required roughly 10 to the 55th ergs of energy to inflate, comparable to the combined explosions of about 100,000 supernovae. If Sagittarius A star powered this event, the outburst likely occurred somewhere between 4 million and 17 million years ago. On cosmic timescales, that happened only yesterday. But the evidence does not end there. In the year 2020, the German-Russian Extended Röntgen Survey with an imaging telescope array detected even larger structures surrounding the galaxy. These immense formations, now known as the Extended Röntgen Survey, with an imaging telescope array bubbles, stretch nearly 45,000 light-years above and below the galactic plane. Whether they record the same eruption viewed differently or preserve evidence of an even older event remains uncertain. Either possibility points toward an energetic past. Other clues surround the galactic center as well. Astronomers have mapped the galactic center lobe, an enormous region filled with radio-emitting plasma. Nearby, long non-thermal radio filaments thread through space almost perpendicular to the galactic plane. Non-thermal simply means their energy comes from highly accelerated particles rather than ordinary heat. Together, these remarkable structures fit naturally within a picture of repeated outflows emerging from the central regions over immense spans of time. Computer simulations deepen that picture. They show that even if Sagittarius A star consumed matter at only a fraction of the rate observed in active galaxies, the consequences would spread across the Milky Way. Powerful winds and radiation could heat vast reservoirs of gas, pushing much of that material away before it condensed into new generations of stars. Astronomers call this process active galactic nucleus feedback, meaning the central engine regulates the future growth of its own galaxy through the energy it releases. But that influence extends far beyond the center itself. The Milky Way currently forms only about 1 to 2 solar masses of new stars each year. Part of that modest pace may reflect gas that was heated or expelled long ago, leaving less raw material available for future star formation. When you consider the galaxy surrounding us today, you may actually be seeing the enduring aftermath of a powerful awakening whose effects continue to shape every spiral arm. Stand for a moment within only a few light years of Sagittarius A star, and the familiar idea of empty space quickly disappears. Around you lies one of the busiest environments in the Milky Way, where massive stars race along tight orbits, powerful stellar winds collide, magnetic fields twist through heated plasma, and drifting dust encounters an immense gravitational influence that never truly relaxes. The greatest supply of material comes from a remarkable population of about 30 Wolf-Rayet stars circling between roughly zero point 0.1 and zero point 0.5 light-years from the center. A Wolf-Rayet star is an evolved, extremely massive star shedding its outer layers at tremendous speed. Each loses about 100,000th of a solar mass every year, together pouring vast quantities of ionized gas into the surrounding region. Ionized gas simply means atoms have lost electrons, allowing the gas to respond strongly to magnetic fields. But very little of that material reaches its destination. Computer simulations following these stellar winds reveal a restless environment where streams of gas collide, generate powerful shock waves, and blend into an enormous reservoir heated to between 10 million and 100 million Kelvin. At such extraordinary temperatures, particles move so rapidly that much of the gas possesses enough energy to escape instead of falling inward. Gravity competes constantly against motion, and motion often wins. Observations from the National Aeronautics and Space Administration Chandra X-ray Observatory support this picture in remarkable detail. After accumulating a total observing time of about 3 million seconds, the telescope mapped the surrounding hot gas and found that the amount of material reaching the event horizon is roughly 100 to 1,000 times lower than the amount flowing through larger distances. Most of the gas is diverted or expelled long before completing the journey, matching predictions from the advection-dominated accretion flow model, a theory describing extremely inefficient feeding around faint black holes. Magnetic fields add another layer of complexity. Near the event horizon, their strength may reach between 100 and 1,000 microgauss, greatly exceeding the values typical across much of the galactic disk. These invisible fields help guide charged particles, influence the shape of the accretion flow, and likely participate in the sudden flares we explored earlier. They may also assist in driving material outward, rather than allowing gravity complete control. Radio observations using very long baseline interferometry have resolved this inner environment to astonishing precision, revealing an uneven, constantly changing emission region only a few Schwarzschild radii from the event horizon. Its brightness shifts over timescales, matching the orbital motion of gas near the innermost stable circular orbit, the closest path where matter can circle without immediately plunging inward. For a non-rotating black hole, this boundary lies about 3 Schwarzschild radii from the center. In Sagittarius A star, that corresponds to roughly 37 million kilometers, which is about 23 million miles, close to 1/4 of the average distance between Earth and the Sunday. But once material crosses this final stable orbit, every remaining path leads inward, and the event horizon is reached within only a matter of hours. There comes a point in every journey toward a black hole where the mathematics continues, but certainty begins to fade. We can calculate the paths of stars, trace the motion of glowing gas, and estimate the shape of spacetime with remarkable precision. But beyond one invisible boundary, our most successful theories stop agreeing with one another. That boundary is the event horizon. If Sagittarius A star truly is a black hole, its event horizon lies about 12.4 million kilometers from the central singularity, which is about 7.7 million miles. According to general relativity, once anything crosses this surface, no light, particle, or message can ever return to the outside universe. The event horizon is therefore not a physical wall. It is the limit beyond which every possible future path leads deeper inward. Surprisingly, you would notice very little at the crossing itself. Because Sagittarius A star is so massive, the difference in gravity between your head and your feet at the event horizon would remain relatively modest. The stretching effect, known as tidal force, becomes overwhelming much farther inside. Crossing the boundary would feel uneventful from your own perspective, but every possibility of communicating with the universe behind you would already be gone forever. But another problem immediately appears. Quantum mechanics insists that information describing every physical system can never truly disappear. Even when matter changes form, the underlying information must remain preserved. General relativity reaches the opposite conclusion. Once information passes through the event horizon, it becomes permanently inaccessible. These two foundational theories have each passed countless experimental tests, yet here they produce incompatible answers. This conflict is known as the information paradox. In the year 1974, Stephen Hawking introduced an astonishing idea that transformed the debate. He showed that quantum effects near an event horizon should cause black holes to emit an extremely faint glow, now known as Hawking radiation. Over immense periods, this radiation slowly carries energy away, allowing black holes to lose mass and eventually evaporate. Some physicists suggest the missing information may emerge within this radiation in an extraordinarily scrambled form. For Sagittarius A star, however, the effect is unimaginably weak. Its Hawking radiation temperature would measure only about 15 hundredths of 1 trillionth of 1 trillionth of 1 Kelvin. This is vastly colder than the cosmic microwave background, the ancient radiation left behind by the early universe. Any Hawking radiation from Sagittarius A star is completely overwhelmed by its surroundings and remains impossible to detect. The timescale stretches even further beyond imagination. If completely isolated and receiving no additional matter, Sagittarius A star would require about 2 multiplied by 10 raised to the power of 83 years to evaporate. By comparison, the universe itself is only about 13.8 billion years old. But the deeper mystery survives every calculation. Until we discover a successful theory of quantum gravity, one capable of uniting quantum mechanics with general relativity, the true nature of whatever lies beyond the event horizon remains beyond the reach of reliable physics. Certainty becomes surprisingly fragile when we reach the very center of our galaxy. We have measured the gravity with remarkable precision, followed stars for decades, and reconstructed the compact glow surrounding the central object. But none of those achievements directly reveals what occupies the deepest region itself. They describe its influence. They do not completely identify its nature. The standard picture remains the black hole predicted by general relativity. In that description, an event horizon surrounds a singularity, a point where density and space-time curvature become formally infinite. Yet many physicists suspect that this singularity signals the limits of the mathematics rather than the limits of nature. The equations may simply be missing new physics that emerges under such extraordinary conditions. But several alternative ideas attempt to fill that gap. One proposal is the gravistar, short for gravitational vacuum star, introduced by Powell Mazur and Emil Modula in the early years of the 21st century. Instead of collapsing into a singularity, the interior becomes a region filled with a form of repulsive vacuum energy. Around it lies an extremely thin shell of ultra-dense matter. From a great distance, its gravity could appear almost identical to that of a black hole, making observational differences exceptionally difficult to detect. Another possibility is the boson star. Bosons are particles capable of occupying the same quantum state together, unlike ordinary matter particles that resist such crowding. A sufficiently large collection could settle into a stable quantum configuration, creating an object with enormous density while avoiding both a singularity and a true event horizon. The shadow surrounding such an object might differ slightly from that of a black hole, although present observations cannot clearly separate the two possibilities. But the ideas become even more unusual. General relativity also permits wormholes, tunnels linking distant regions of space-time. Stable wormholes would require exotic matter possessing negative energy density, something never observed in the required amounts. Even so, theoretical studies have shown that under specific assumptions, the throat of a wormhole could produce an image resembling the central shadow already observed. Some researchers instead favor regular black holes. These models preserve the event horizon while replacing the singularity with a compact region of extremely high yet finite density. Variants proposed by physicists including James Bardeen and Sean Hayward avoid infinite values while remaining broadly compatible with Einstein's equations. The fermionic dark matter core discussed earlier joins this growing collection. It reproduces the observed stellar motions and can generate a shadow matching current observations without requiring either an event horizon or a singularity. But matching today's evidence does not guarantee correctness. It simply means the available measurements remain incomplete. Future observations may finally separate these competing pictures. Planned upgrades to the Event Horizon Telescope include longer observing baselines, extending beyond Earth's diameter through space-based interferometry, meaning multiple widely separated telescopes working together as one enormous virtual instrument. With sharper resolution reaching well below a single Schwarzschild radius, we may eventually learn whether the heart of the Milky Way contains the object we have imagined for decades or something even stranger. Few places in the universe allow us to examine the foundations of physics as directly as the crowded heart of our own galaxy. Every observation gathered from this remarkable region carries value beyond astronomy alone. As you follow the motions of stars and the behavior of glowing gas, you are also watching nature perform experiments that no laboratory on Earth could ever reproduce. The strongest examples are the rapidly orbiting stars surrounding Sagittarius A. Among them, the stars known as S2 and S62 sweep through gravitational fields billions of times stronger than the pull we experience at Earth's surface. Their paths become living measurements of gravity itself. By tracing these orbits with extraordinary precision, astronomers compare the predictions of Isaac Newton with those of Albert Einstein, especially where the differences become greatest. This strong field regime, meaning the environment where gravity becomes exceptionally intense, offers one of the most demanding examinations of general relativity. But the testing has only begun. During the closest approach of S2 in the year 2018, astronomers confirmed both gravitational redshift, meaning light loses energy while escaping gravity, and Schwarzschild precession, the gradual rotation of an orbital path predicted by general relativity. Those observations matched theory remarkably well. Future close passages by stars traveling even nearer to Sagittarius A may reveal subtler effects, including frame dragging, where a rotating mass twists spacetime around itself, or perhaps expose small departures from the familiar Kerr description of spinning black holes. Another leap forward came from the instrument known as gravity on the Very Large Telescope Interferometer. Interferometry combines light collected by multiple telescopes into a single virtual instrument with far greater resolving power than any individual telescope alone. This achievement has allowed astronomers to follow some of the faintest known stars near the galactic center while measuring their motions with astonishing accuracy. Planned improvements promise to detect even dimmer stars traveling along tighter orbits. But stars tell only part of the story. The central region is also expected to contain between 10,000 and 20,000 stellar mass black holes gathered over billions of years. Through dynamical friction, a gradual slowing caused by countless gravitational encounters with surrounding stars, these compact remnants slowly drift toward the galactic center. Most remain completely invisible by themselves. Together, however, they subtly influence stellar motions and shape the environment surrounding Sagittarius A. A small number of nearby X-ray binary systems, where one object draws matter from a companion star, may already reveal some of these hidden residents. The galactic center is equally important in the search for dark matter. Many theoretical models predict the invisible material should become increasingly concentrated toward the galaxy's core, creating a dense spike that could generate detectable gamma rays if dark matter particles decay or destroy one another. No confirmed signal has appeared despite increasingly sensitive observations, but every new measurement sharpens the limits. Each night of observation deepens several investigations at once. We test gravity, quantum theory in curved spacetime, the behavior of hot plasma, the evolution of stars, and perhaps the true nature of dark matter, all while studying a single remarkable destination. The story of Sagittarius A continues to evolve because our instruments continue to evolve with it. Each improvement sharpens our view by only a small amount, yet those small gains often reveal entirely unexpected details. You and we stand at a moment when several new observatories are preparing to examine the galactic center with a level of precision that was impossible only a few years ago. The Event Horizon Telescope is already expanding through additional observing stations across Greenland, France, and Africa. Every new station creates additional observing baselines, meaning more independent telescope pairings that improve image quality and reduce uncertainty during computational reconstruction. With each observing campaign, astronomers expect cleaner images and more reliable measurements of the compact emission surrounding Sagittarius A. But an even greater leap is already being planned. The next generation Event Horizon Telescope seeks to include many more observing sites and, eventually, antennas placed in space. Extending the array beyond Earth's diameter would dramatically improve angular resolution, allowing structures only a few Schwarzschild radii across to become distinguishable. A Schwarzschild radius is the distance defining the event horizon of a non-rotating black hole. At this scale, astronomers hope to observe the elusive photon ring, an extremely thin circle of light created by photons that loop around the compact object one or more times before finally escaping toward us. General relativity predicts its shape with remarkable precision. Even a slight deviation could point toward entirely new physics. But radio images represent only one path forward. The upgraded Gravity Plus instrument at the Very Large Telescope Interferometer will search for even fainter stars orbiting closer to Sagittarius A. Some may complete an orbit in less than a single year. Such discoveries would allow increasingly demanding tests of gravity while tightening estimates of the central object's spin and the geometry of the surrounding spacetime. Another possibility remains especially exciting. Astronomers continue searching for a pulsar orbiting very close to Sagittarius A. A pulsar is a rapidly spinning neutron star that emits remarkably regular flashes of radio waves, behaving almost like a natural cosmic clock. If one were found near the galactic center, the precise arrival times of its pulses would reveal the surrounding gravitational field with extraordinary detail. Dense gas between Earth and the galactic center has complicated this search because it scatters radio signals before they reach us. But future facilities may overcome that obstacle. The Square Kilometre Array, now under construction across South Africa and Australia, is expected to deliver the sensitivity needed to detect previously hidden radio sources while studying the galactic center in unprecedented detail. It may discover long-sought pulsars, trace the recently detected wind flowing away from Sagittarius A, and reveal structures within the surrounding accretion environment that remain invisible today. Future gravitational wave observatories could add another entirely different perspective. They may eventually detect stellar mass black holes or neutron stars spiraling into Sagittarius A, allowing spacetime itself to announce its structure through ripples moving across the universe. Every new observational window opened onto the galactic center has challenged previous expectations. There is every reason to believe the next generation will continue that tradition. Nothing surrounding Sagittarius A will remain unchanged forever. Even the vast spiral structure carrying our solar system through space is part of a much larger journey. You and we can follow that path far beyond the lifetime of our sun into an era when the familiar outline of the Milky Way has disappeared and another galaxy has become inseparable from our own. The Milky Way and the Andromeda Galaxy are drawing together at roughly 110 kilometers per second, which is about 68 miles per second. Careful gravitational modeling indicates their first close encounter will occur in about 4.5 billion years. Their interaction will continue across several billion additional years as tidal forces stretch, distort, and eventually blend both galaxies into a single giant elliptical system. But the stars themselves are unlikely to collide. The immense distances between individual stars make direct impacts extraordinarily rare. Instead, gravity reshapes entire stellar populations, while vast clouds of gas lose energy and drift toward the common center. There, another process slowly begins. Each galaxy carries a supermassive black hole, and these enormous objects gradually spiral inward through dynamical friction, a process in which countless gravitational encounters rob them of orbital energy until they form a binary pair circling one another. The central black hole of the Andromeda Galaxy is estimated to contain about 100 million times the Sun's mass, roughly 25 times greater than Sagittarius A. Over millions to billions of years, the orbit of this giant pair shrinks until the two black holes finally merge into a single object with a combined mass of about 104 million solar masses. But the merger itself unfolds with astonishing power. As the orbit tightens, the The system releases enormous gravitational waves, ripples traveling through spacetime itself. The final burst carries away tremendous energy and can produce a gravitational recoil, often called a kick, that may send the merged black hole racing away from the exact center of its new galaxy at speeds reaching hundreds or even thousands of kilometers per second, which is about hundreds or even up to roughly 621 miles per second. The surrounding galaxy will respond as well. Gas clouds and stars disturbed during the collision are expected to funnel toward the merged black hole, dramatically increasing the available fuel. For a time, the galactic nucleus could blaze as an active galactic nucleus, releasing vastly more energy than the Milky Way has generated for hundreds of millions of years. Long before that distant transformation, our own sun will have expanded into a red giant before ending its life as a white dwarf. Earth will almost certainly have become uninhabitable around 5 billion years from now, as the swelling sun consumes or scorches the inner solar system. But even that spectacular merger is temporary. Across an almost unimaginable future, stretching toward roughly 2 times 10 raised to the 83 years, the merged black hole would slowly lose mass through Hawking radiation if no additional matter remained to feed it. Whether every piece of information carried into that object ultimately survives in some hidden form remains one of the deepest unanswered questions that the universe still keeps beyond our reach. Every observation we make begins with an unavoidable delay. Before any image reaches us, before any radio signal is collected, time has already shaped the story. When you look towards Sagittarius A, you are seeing light that began its journey about 26,000 years ago during the late Paleolithic period, when anatomically modern humans were gradually spreading across continents beneath unfamiliar skies. That delay changes everything. The object we study today no longer truly exists in its observed state. Across those 26,000 years, Sagittarius A may have consumed a wandering cloud of gas, captured an unfortunate star, or shifted into a different pattern of accretion. We simply cannot know. Whatever has happened since then remains hidden behind the distance separating us from the galactic center, and every new observation still belongs to an ancient chapter of its history. But distance is only the first barrier. The event horizon creates a deeper one. It marks the boundary beyond which no signal can ever return. Light cannot escape. Particles cannot escape. Information that crosses inward can no longer communicate with the outside universe. Even an instrument of impossible perfection would reveal nothing beyond that limit because no message exists that could complete the journey back to us. The uncertainty extends further still. General relativity predicts that every path inside the event horizon ultimately leads inward, where familiar descriptions of space and time lose their usefulness. Whether a true singularity exists or whether some unknown quantum process replaces it remains beyond direct observation. We may construct mathematical models, compare competing theories, and test every prediction outside the horizon, yet the interior itself refuses experimental confirmation. Another possibility carries similar uncertainty. If the compact object at the galactic center were instead composed of dark matter, the particles responsible might interact with ordinary matter only through gravity. In that case, they would remain effectively invisible to every detector humanity has conceived. Their existence would be inferred from their gravitational influence alone, leaving their true nature permanently uncertain. But even confirmed predictions can remain unreachable. Hawking radiation should emerge from every black hole through quantum effects near the event horizon. For Sagittarius A, The expected temperature is roughly 1.5 multiplied by 10 raised to the negative 14 Kelvin. That is unimaginably colder than the cosmic microwave background, whose temperature is about 2.7 Kelvin, or 29 degrees below 0 Celsius, or 420 degrees below 0 Fahrenheit. The surrounding universe completely overwhelms such an extraordinarily faint signal. Perhaps the greatest boundary lies within our own understanding. A complete theory of quantum gravity, one that successfully unites quantum mechanics with general relativity, has not yet been discovered. Without it, some of the deepest questions surrounding Sagittarius A remain suspended between mathematics and reality. We continue observing because every answer sharpens the mystery, reminding you and us that the most carefully studied place in our galaxy still guards truths beyond the reach of any telescope. Some realities become harder to understand the more accurately we measure them. As our instruments sharpen and our calculations improve, the numbers describing Sagittarius A star grow increasingly precise. Yet precision does not always bring familiarity. Instead, it reveals how completely this object exists beyond ordinary human experience. Sagittarius A star contains about 4.15 million times the mass of our Sunday. Expressed another way, its mass is roughly 8.26 multiplied by 10 raised to the 36 kilograms. Earth, by comparison, weighs about 5.97 multiplied by 10 raised to the 24 kilograms. The difference is staggering. The black hole outweighs our entire planet by roughly 1.4 trillion times, a ratio so immense that even comparison begins to lose meaning. Its size deepens that impression. The event horizon extends about 12.4 million kilometers from the center, which is about 7.7 million miles. That radius is far larger than the Sun itself, whose radius measures about 696,000 kilometers, which is about 432,000 miles. Yet it remains comfortably inside the orbit of Mercury, whose closest distance from the Sun is about 58 million kilometers, which is about 36 million miles. A boundary capable of enclosing the inner solar system is created by an object occupying almost no visible space at all. Distance reshapes our perspective as well. The galactic center lies about 26,000 light years away. Every photon arriving today began its journey long before recorded civilization. It departed while our ancestors still lived entirely without cities, agriculture, or written language. We never observe Sagittarius A star as it exists now. We always witness its distant past. But the strangest comparisons emerge near the event horizon. If you could somehow remain motionless exactly at that boundary and shine a flashlight directly outward, the beam would never truly escape. At the event horizon, the outward motion of light is matched exactly by the inward curvature of space-time itself. From the outside, that light would appear suspended forever, never breaking free and never returning. Nearby stars reveal another extraordinary scale. During its closest approach, the star known as S2 races through space at roughly 7,650 kilometers per second, which is about 4,754 miles per second. At that speed, you could cross the distance between Earth and the Moon in roughly 5/100ths of a second, or circle Earth in about 6/1000ths of a second. Yet crossing the event horizon of Sagittarius A star would feel unexpectedly ordinary. The difference in gravity between your head and your feet would amount to only about 1,000th of Earth's surface gravity. A smaller black hole would tear you apart instantly. This one would not. When astronomers measured the light from S2 during its closest passage in 2018, they found its spectrum shifted by the equivalent of about 200 kilometers per second, which is about 124 miles per second. Exactly as general relativity predicted, each measurement sharpens our understanding, but together they point toward a deeper truth. The universe has created something that can be measured with remarkable precision while remaining profoundly resistant to genuine human intuition. Some discoveries begin with a question, others begin with a mistake. Our understanding of Sagittarius A star belongs to the second kind, growing across nearly 90 years through countless observations, unexpected clues, and remarkable persistence. What finally emerged was not the result of one breakthrough, but of generations of people slowly assembling a picture of something no human being could ever visit. The story opened in the early 1930s with Carl Jansky, an engineer working for Bell Telephone Laboratories. His task was practical rather than astronomical. He was searching for sources of interference affecting long-distance telephone communication. Instead, he detected a faint radio hiss that drifted across the sky with astonishing regularity. It matched neither weather nor the Sunday. The source lay far beyond the solar system, revealing for the first time that the universe itself produced radio waves. But the discovery seemed commercially useless. Bell Telephone Laboratories chose not to continue the work, leaving Jansky's unexpected finding without immediate follow-up. Even so, his observations founded the entirely new field of radio astronomy. Decades later, increasingly powerful radio telescopes would identify Sagittarius A star, uncover the remarkable activity surrounding it, and eventually measure the mass of the central object with extraordinary precision, reducing the uncertainty to less than 0.5%. Another chapter unfolded through patience rather than chance. Beginning in the early 1990s, Reinhard Genzel and his colleagues at the Max Planck Institute used the New Technology Telescope before expanding their work with the Very Large Telescope in Chile. Around the same period, Andrea Ghez and her team began observing the galactic center with the W.M. Keck Observatory in Hawaii. Both groups developed adaptive optics, a technique that measures atmospheric distortion and continuously reshapes telescope mirrors to restore sharp images almost instantly. Year after year, they watched. Their teams tracked thousands of stars near Sagittarius A star. Among them, the fast-moving S stars revealed invisible gravity at work. After decades of careful measurement, both research groups independently reached nearly identical conclusions about the mass of the hidden object. Such agreement carried unusual weight because no direct experiment could confirm the answer. The evidence came entirely from nature itself, but an image still remained beyond reach. That challenge demanded something unprecedented. The Event Horizon Telescope collaboration joined more than 300 scientists, representing about 80 institutions across 21 countries. 8 observatories, spread across Earth, observed simultaneously, while atomic clocks, accurate to within about 1 second over 100 million years, synchronized every recorded signal. Those separate observations were later combined into a virtual telescope nearly as wide as our planet. The observations were completed during 2017. The picture required roughly 2 years of processing before its release during 2022. Multiple independent imaging methods were compared to ensure the result reflected the data rather than the assumptions of any single algorithm. Across nearly a century, every advance depended upon curiosity joined with extraordinary patience. You, and we inherited that long chain of careful work, allowing us to glimpse an object that continues to challenge every instrument, every equation, and every attempt to fully understand its true nature. Imagine trying to build a lasting home where every nearby neighbor constantly reshapes the landscape. That is the challenge presented by the galactic center. As we compare this crowded environment with our own corner of the Milky Way, you begin to understand why astronomers consider it among the least welcoming places for complex life. The obstacles arise from every direction at once, combining gravity, radiation, and relentless cosmic activity into a setting unlike almost anywhere else in our galaxy. Within the central parsec, a region measuring about 3.3 light years across, the density of stars reaches roughly 10 million times that of the solar system's neighborhood. The average separation between neighboring stars shrinks from several light years to only a matter of light days. Encounters become common. Stable planetary orbits become increasingly difficult to preserve as passing stars tug on one another through gravity, gradually disturbing or even ejecting planets from the systems where they first formed. But gravity is only one hazard. Sagittarius A star regularly produces infrared flares, often every day, while stronger bursts of high energy radiation occasionally erupt in the form of powerful X rays. During 2019, astronomers observed an infrared flare roughly 75 times brighter than its usual level. Around the same region, nearby exploding stars and energetic gas release additional streams of radiation. Any planetary surface within a few light years would receive doses millions of times greater than those reaching Earth's surface, enough to damage complex organic molecules and gradually erode planetary atmospheres. The surrounding stellar population creates further dangers. Massive stars live brief lives before ending as supernova explosions. Because the galactic center contains so many of these stars, such explosions occur far more frequently than they do near our own Sunday. A supernova occurring within about 30 light years of a planet could expose it to intense gamma rays and cosmic rays, delivering enough energy to trigger widespread biological damage and even global extinction events. But life has surprised us before. On Earth, living organisms thrive beside deep-sea hydrothermal vents, inside intensely acidic lakes, and within the cooling pools of nuclear reactors. Each discovery expanded our understanding of biology beyond earlier expectations. Could unfamiliar forms of life endure conditions surrounding Sagittarius A star by using entirely different chemistry or extraordinary protective adaptations? We simply do not know. Current evidence neither confirms nor completely excludes that possibility. Astronomers instead focus their hopes farther from the center. The idea known as the galactic habitable zone proposes that complex life is most likely to emerge between roughly 7,000 and 9,000 parsecs from the galactic center, where heavy elements remain abundant enough for rocky planets while destructive events become far less common. Our solar system, located around 8,200 parsecs from the center, sits remarkably close to that favorable range. But perhaps the greatest lesson is perspective. By understanding why Sagittarius A star presents such profound challenges for life, you and we also gain a clearer appreciation of the unusual stability that has allowed our own world to endure for billions of years. Every journey through the night sky begins from a place that is itself already moving. As you stand beneath familiar stars, the ground beneath your feet, the sun above it, and every planet in our solar system are participating in an orbit that began billions of years ago. We are not standing apart from the Milky Way. We are passengers within it, carried around Sagittarius A star by the gravity that binds the entire galaxy together. Astronomers estimate that between 200 billion and 400 billion stars belong to the Milky Way. Every one of them follows a path ultimately shaped by the enormous mass concentrated at the galactic center. The Sun travels along an orbit roughly 26,000 light-years from Sagittarius A star. Completing one full circuit requires about 225 million years, an interval sometimes called a cosmic year or a galactic year. Since the solar system formed about 4.6 billion years ago, the Sun has completed only about 20 of these immense revolutions. That is remarkably few. During each orbit, the heart of the galaxy continued to evolve. Rates of star formation rose and fell. Vast structures, such as the enormous gamma-ray bubbles stretching above and below the galactic plane, formed during energetic episodes. The flow of gas toward Sagittarius A star almost certainly changed many times, producing periods of greater and lesser activity while the solar system remained far beyond the crowded central regions. But our location is unusually forgiving. The solar system resides within the local arm, a comparatively small spiral feature where neighboring stars are separated by generous distances. Close stellar encounters are exceptionally rare over the timescales of human civilization. That long-lasting stability has allowed planetary orbits to remain largely undisturbed, giving Earth billions of years to preserve oceans, maintain a relatively stable climate, and support increasingly complex forms of life. Each year, during the month of December, Earth, the Sun, and the galactic center briefly align from our perspective. The Sun appears against the direction of Sagittarius, placing Sagittarius A star almost directly beyond it. Even then, the additional distance across Earth's orbit is insignificant compared with 26,000 light-years. On a galactic scale, our position barely changes at all. But distance has been our ally. Had Sagittarius A star been only a few hundred light-years away, its energetic environment could have transformed our cosmic neighborhood into a far more hostile place. Had it been vastly farther away, resolving the motions of individual stars around it might never have been possible. Instead, we occupy a fortunate middle ground, close enough to investigate one of nature's greatest mysteries while remaining safely beyond its most dangerous influence. Looking toward Sagittarius on a clear night, therefore, carries an unexpected meaning. You and we are gazing toward the gravitational heart that has guided our galaxy since its earliest history, an unseen anchor around which our own existence has completed only a handful of majestic circles. There is an unusual thought waiting at the heart of our galaxy. Every star you have ever seen, every cloud of glowing gas, every world that circles a distant sun, and our own solar system all trace immense paths around a single central object. Yet the very place that anchors this grand structure may forever deny us direct knowledge of what lies within. The event horizon marks far more than a distant destination. It is a causal boundary, meaning the chain of cause and effect that carries information across the universe can no longer reach outward once that boundary has been crossed. No light escapes, no signal returns. No future technology, regardless of its sophistication, can overcome this limit if our current understanding of space-time is correct. The interior is therefore separated from us in a way unlike any mountain, planet, or galaxy. But this kind of mystery stands apart from every other scientific unknown. We have never drilled into the deepest layers beneath the surface of Venus, yet instruments could someday accomplish that task. The first generation of stars disappeared billions of years ago, yet their descendants still preserve clues about their composition. Even regions beyond today's observable universe remain subjects of theoretical discussion because changing cosmic conditions could alter what becomes visible over unimaginable spans of time. The interior, beyond an event horizon, offers no similar possibility. According to general relativity, there is no path by which that information can ever rejoin our observable universe. Still, the search continues. Astronomers do not expect to peer beyond the event horizon itself. Instead, they examine the threshold surrounding it, the shadow, the glowing gas that circles nearby, and the remarkable motions of neighboring stars. Each reveal details about the geometry of spacetime immediately outside the boundary. Every observation refines the picture, allowing us to test whether nature truly follows the predictions of our best theories. But even those theories remain unfinished. General relativity predicts that matter ultimately reaches a singularity, a place where density becomes infinite and the equations themselves lose meaning. Most physicists suspect that infinity signals an incomplete description rather than physical reality. A future theory of quantum gravity, meaning a framework that unites gravity with the rules governing the smallest particles, may replace that singularity with something finite and fully physical. What that replacement might be remains unknown. Perhaps Sagittarius A star contains such a quantum structure. Perhaps it conceals an entirely different compact object that only imitates a black hole from the outside. Every careful observation narrows the possibilities, yet none has erased the deepest uncertainty. That uncertainty carries an unexpected beauty. The gravitational center of our galaxy is also the boundary of our present understanding. Everything we have learned throughout this journey points toward that remarkable truth. We inhabit a galaxy whose unseen anchor continues to define its structure while reminding you and we that the map of knowledge, however vast it becomes, will always possess an edge waiting to be explored. From a single point near the middle of our galaxy, an extraordinary chain of understanding spreads across the universe. Sagittarius A star is more than a destination for telescopes. It serves as a natural laboratory where gravity, time, matter, and light reveal how the deepest laws of nature operate under conditions that cannot be recreated anywhere on Earth. As we study this one object, you and we are also studying the architecture of countless other galaxies beyond our own. Every successful prediction confirmed by the stars orbiting Sagittarius, a star strengthens general relativity, the theory describing how mass bends spacetime and guides the motion of planets, stars, and black holes alike. Those precise stellar orbits do not apply only to our galactic center. They also describe stellar mass black holes only a few kilometers across, which is about 1.9 miles, and the enormous black holes containing tens of billions of solar masses inside the largest galaxies ever discovered. A measurement made here echoes across the observable universe. But gravity is only part of the story. The unusual behavior surrounding Sagittarius A star has inspired new ideas about dark matter, the unseen material whose gravity shapes galaxies while remaining invisible to direct detection. One proposal suggests an extremely dense collection of dark matter particles could imitate many properties expected from a black hole. Comparing these competing models has transformed the galactic center into one of nature's most demanding experiments, pushing physicists toward a clearer understanding of how dark matter may gather and evolve over cosmic time. The surrounding environment has also rewritten the history of our own galaxy. The enormous Fermi bubbles, Giant lobes of energetic particles extending far above and below the Milky Way reveal that the galaxy experienced an energetic episode millions of years ago. Their discovery replaced the older picture of a permanently tranquil galaxy with one that continues responding to ancient outbursts whose consequences remain visible today. Other mysteries continue reshaping astronomy. Young stars occupy regions where intense gravity should make their formation extremely difficult. Their presence has forced astronomers to revise long accepted ideas about how stars emerge close to supermassive black holes. Meanwhile, the remarkably modest activity of Sagittarius A star helps explain why most giant black holes in today's universe remain comparatively inactive, despite possessing enormous gravitational influence. But perhaps the greatest lesson reaches beyond observation itself. Black holes have inspired entirely new approaches to fundamental physics. The information paradox, asking whether information truly disappears inside a black hole, has encouraged ideas such as the holographic principle, the proposal that information filling a volume of space may instead be encoded across its boundary. Another concept links quantum entanglement, meaning deep connections between particles separated by distance, with hypothetical bridges through spacetime known as wormholes. Our observable universe contains an estimated 2 trillion galaxies. Each almost certainly possesses its own central giant. Sagittarius A star is simply the closest example. Yet, through its motions, mysteries, and remarkable consistency with physical law, it allows you and we to glimpse principles governing a universe far larger than human imagination was ever shaped to comprehend. Every journey eventually arrives at a place where measurement gives way to perspective. After everything we have explored, we find ourselves returning to a simple truth. The galaxy we call home revolves around a region almost entirely hidden from direct view. This is not symbolism, it is the physical arrangement of the Milky Way itself. Its spiral arms, glowing clouds, wandering stars, and every planetary system, including our own, move through immense cycles around a center whose deepest interior remains forever inaccessible. The light reaching your eyes from Sagittarius A star today began its journey about 26,000 years ago. During that distant age, people painted cave walls across what are now France and Spain. Others crossed exposed land bridges into the Americas. Language, art, and shared memory were taking stronger shape. Those early communities could never have imagined that their descendants would eventually build instruments capable of tracing the invisible heart of the galaxy from 26,000 light years away. But that is exactly what happened. Radio telescopes first detected whispers from the galactic center. Infrared observatories followed stars weaving through powerful gravity. Then a worldwide network of observatories acted together as a single instrument spanning nearly the diameter of Earth. The shadow emerged, stellar paths were measured, the central mass was calculated. Winds flowing from the surrounding material were identified. Every answer strengthened our understanding while revealing deeper questions waiting beneath it. Science has never promised complete certainty. Instead, it offers an honest conversation with reality, even when reality refuses to become simple. Sagittarius A star has shown us what several million solar masses gathered into a remarkably compact region can reveal about gravity, space-time, and the history of galaxies. Yet it continues to surprise us with behavior that remains calmer, older, and more intricate than many early predictions suggested. The Milky Way continues its endless rotation. Stars complete their ancient paths. The central object waits through ages that dwarf civilizations. Most of the time it shines only faintly. Sometimes it brightens for a brief interval before settling once more into relative stillness. Those changing moments unfold across billions of years, while human history occupies only the smallest fraction of that immense timeline. But perhaps the greatest discovery is not hidden inside the event horizon. It is found within the remarkable path that brought us here. A species living on a rocky world around an ordinary star learned to detect motions too small for the eye, combine observations from across the planet, and uncover the invisible anchor of its own galaxy. Our map now reaches the threshold where present knowledge ends. Beyond that boundary, questions remain, yet the search itself has become part of the universe it seeks to understand, and you and we are fortunate enough to witness that story while it is still unfolding.